Moving on in question 18.18, let's take a look at B. I'm going to zoom in on this one here a little bit. Let's see, we've got a methyl group, which we saw in the first problem, is a weak activator. So I'm just going to put here a weak activator, and it is ortho-para directing. So that means that it's directing to this position, which is blocked, this position, which is blocked, but this position, which is open. So I'll highlight that one in yellow. And if we look at the two nitro groups, and this compound is just a regioisomer of, or just an isomer of A. So these are strong deactivators, and therefore these are both meta-directors. So that means that this one is going to direct to this position, and the other one is going to direct to this position. But remember, we go with whatever is the stronger director, and the methyl group is an activator, and so the position where the substitution will occur is the one that's highlighted in yellow. Let's move on to the next one. We've got a methyl group. Again, I'm going to address that first since we've talked about methyl groups already. We know that methyl groups are alkyl groups. They are weak activators, so weak activators. Therefore, this is ortho-para directing. But then we have an ester here, and we have an oxygen attached directly to our aromatic ring. Now, we know that this is a moderate activator, which is going to be ortho-para directing. And then when I have the carbonyl of an ester directly attached to my aromatic ring, this is a moderate deactivator, which is meta-directing. Well, if I evaluate all of these, this one is going to be the strongest activator, and it's ortho-para directing. Well, you can see that this ortho position is blocked, as is the para position, but this ortho position is not. And therefore, the position that I have highlighted in yellow is the position where electrophilic aromatic substitution will occur. All right, let's look at the last one. We have a nitrile, and we saw that nitriles were moderate deactivators. So moderate deactivator, that means it's a meta-director. And then, of course, we have the two methyl groups. They are both weak activators, so weak activators, and they are going to be ortho-para directors. Well, the activators are stronger, right, because they're activating, not deactivating. They are both going to direct to their ortho positions. Both of their para positions are blocked, and the nitrile is also directing to these two positions. So that means I'm only going to direct to one of them. I'm going to assume mono substitution. So I could highlight either this one or I could highlight this one. It doesn't matter. But that is where the electrophilic aromatic substitution reaction will occur. So again, what did we do? We looked at table 18.1. Okay. And whenever we had something that was an activator, it took precedence over something that was a deactivator. And when we had more than one activator, the stronger of the two activators is the one that dictated where the substitution will occur on our aromatic ring. Let's move on from there and take a look at 18.20. For each of the following compounds, determine the position that is most likely to be the site of an electrophilic aromatic substitution. I'm going to highlight three of these sites, and I'm going to ask you, so I'll put one in yellow, one in green, and one in blue. Could anybody tell me which one of these sites would be the preferred site of electrophilic aromatic substitution? Okay, I got somebody saying the one in blue. Okay, let me ask you the question a different way. Out of all the groups that are on here, we've got a hydroxyl, a nitro, and a methyl. Which one of those would be the strongest activator? There's only one of them that's a strong activator. You might have to refer back to table 18.1. It's the hydroxyl, right? The hydroxyl is the only strong activator. So we can even take a shortcut because we know this is deactivating and this is a weak activator. Well, the hydroxyl, if I erase all these, the hydroxyl is directing to the ortho positions and the para position. Well, the para position is blocked, and this ortho position is between two groups. So it is not going to be directed to that position. And so the position where the direction is going to occur is at the one that I have in the red circle. Now, I don't remember which color that was. It was the one that was yellow. So the yellow one is where the activation is going to occur. All right. Let's take a look at the next one. I have a nitro group. Right, I've got a nitro, I've got a methoxy, and I have a bromine. Could anybody tell me which one of these would be the strongest activator? It's the methoxy. Yes, thanks, Skylar. Absolutely. This is the strongest activator, and it's a moderate activator. It's kind of like more like a moderate slash strong activator. Okay, so that means it's going to be what? It's going to be an ortho para director. Well, let's take a look. The para position is blocked. Okay, so that's gone. Then we have two ortho positions. Well, the one right here is between two groups. Therefore, nothing is going to happen there. That means that the electrophilic aromatic substitution is going to occur at this position. All right, let's take a look at the last one. This is a 1,4 disubstituted or a para-substituted compound. Both of them have carbonyls. So this one's kind of an interesting one, right? Because both of the groups are moderate deactivators, right? This is a moderate deactivator, therefore a meta director. So that means it's directing to both of these positions. And this one here is also a moderate deactivator, and it's directing to the meta position, which would be these two. Well, I have two in yellow that are identical, and I have two in green that are identical. Could anybody guess which one would be the one where the electrophilic aromatic substitution would occur? Would it be at one of the yellow positions or the positions I have highlighted in green? Did anybody make a guess about that? Or an educated guess, I should say? I'll give you a clue. It's going to have something to do with this big old tert-butyl group here. Yeah, it's going to be the green position, right? Why? Because this is so bulky. So just based off of steric effects, we can assume that alkylation will predominate at the position in green because of the steric effects, okay? Let's put here, we'll draw an arrow and we'll put because steric effects, right? So if you can't solve it just using table 18.1, what do you go to next? Use your brain, right? Exactly. Use your best hypothesis. And I can see that everybody had the right answer. So you all figured it out, right? Okay, let's take a look at 18.2. Now we're going to get into that whole concept of a blocking group. I'm going to go back a little bit in our slides just to refresh your memory as to what a blocking group is. A blocking group is a sulfonic acid that we install using concentrated sulfuric acid. It can be removed with dilute sulfuric acid. It is a moderate deactivator. So we'll put here moderate deactivator. Do I already have that written? I do. It's a moderate deactivator. And it is a meta director. Well, let's go back to the question. So this is question 18.22. And the question just asks us, can you do this synthesis with or do you need a blocking group? So what about an A? Does anybody have an idea? I'm sure you had time to take a look at it. Does anybody know, do we need a blocking group to do A? Yeah, I agree, Skylar. I think we definitely need a blocking group. Why? Because if you just took this molecule, which is called cumene, if you just took this and treated it with nitric acid and sulfuric acid, what's going to happen? Well, you're only going to get the nitration occurring at the para position, right? Because this is so bulky. So that doesn't get you anywhere near having ortho nitration. So let's erase all that. And what do we have to do first? We're going to have to take that molecule of cumene, okay, this guy here, like this. And the first thing we're going to have to do is install a blocking group. So we're going to use fuming. Sometimes the book says fuming sulfuric acid. Other times it says fuming concentrated sulfuric acid. Either way, it's the same thing. So then we put in our sulfuric acid, or sulfonic acid rather. There's our isopropyl group. It's SO3H. Okay, now we can do the nitration. Why? Because we have this guy who's directing to these two positions, and the isopropyl group is directing to the exact same two positions, right? Which is where we want the nitration to occur. So we're going to treat this with nitric acid and sulfuric acid. Then we end up with our nitro group in the position where we want it, right here. There we go. And then in the last step, we're going to treat it with dilute H2SO4. And that's going to pop that off, and we end up right back to here to our final product. All right. There we go. So that's how we do that transformation. So it's a total of what? 1, 2, 3 steps. What about the second one? So 18.22b. Would you need a blocking group to do 18.22b? If you wanted to brominate there? Cha or no? The answer is no. Yeah, absolutely. Okay, so for the first one, we'll say yes. For the second one, we'll say no. Why? Because the isopropyl group is so bulky that even though it's an ortho para-director, again, since it's so big and bulky that when you treat this with bromine, let me use a different color here. When you treat that with bromine and iron 3 bromide, you end up brominating at the para position. And we'll put here because of steric effect of isopropyl group. And that will be our answer. There you have it, my friends. All right. Well, you notice probably a recurring theme in our class's textbook, and that is whenever we get towards the end of some of these chapters, he likes to put a table together where we have all of the new reactions that we've covered, and there's usually a few nuances that are missing, but let's kind of discuss them all. The first one is bromination, using bromine and aluminum bromide. Of course, you could use or FeBr3, that will work. The same thing with chlorination or FeBr3, right? That works. So for bromination and chlorination. The next one is a nitration, where we use nitric acid followed by sulfuric acid. I also want you to know this reduction here. It's just iron or zinc and HCl, and then followed up by sodium hydroxide, right? Because after the first step, you end up with this, you end up with aniline, which has a positive charge. Okay, so then you treat it with base to make the aniline derivative. Fuming sulfuric acid, and you can put fuming concentrated if you want. They leave it out sometimes. This one here is a Friedel Crafts. Friedel Crafts alkylation. So we'll just put Friedel Crafts alkylation. And the next one is a Friedel Crafts acylation. Okay. You need to know those. So an alkyl halide or an acyl halide and aluminum chloride. Well, what can you do with this? This is a reaction that we haven't really addressed in this chapter yet. This is covered in chapter 17, the last chapter. You remember bromination at the benzoic position. We used NBS and bromosuccinimide. Well, if you use an excess of NBS on a molecule like toluene or a derivative, you get excess bromination. So you end up with this tribromomethyl group. And the reason why that's so important is because this is a strong deactivator. So, and we're going to talk about that in a few minutes, but that's a strong deactivator, which would be meta-directing. What else? We talked about in chapter 17, oxidation at the benzoic position. You just need one hydrogen here, at least. And we said there's a couple of ways to do that. You could either use potassium permanganate and heat, follow that up with water, or you could use chromic acid instead of this. That will work too. So sodium dichromate, sulfuric acid, and water, that would work. And then this reaction here, this last one, this is the Clementine reduction. Clementine reduction. You know, the two types of reduction that we learn or that are on this slide, something that's just kind of interesting, is that the Clementine requires heat, whereas this reduction doesn't require heat. And I would say, you know, that probably depends on the situation, because I've done this reaction a lot, and sometimes you do have to heat it. So if you were to write heat by, it's not the end of the world. Okay, that's for sure. Let's move on with our synthesis strategies, right? Let's say you have all those reactions down pat. You know them frontwards, you know them backwards, you know when to use them. Well, let's say you wanted to make this compound right here. Somebody says, you know what, I'm going to pay you $50,000 if you can make me 1 gram of that. And you're going to say, I'm going to let you do that. Okay, well, how would you make that compound, right? You have an ortho para director here, and you've got a meta director here. Well, which one of those groups would you install first? You'd probably want to put the nitro in first, because it's going to direct to this position. If you put the bromine in first, you're only going to direct to that position. So that's the kind of strategy you want to think about, right? Which group am I going to put in first? Which group am I going to put in last, right? These are considerations that you have to take into account. Now, the next table is kind of an interesting one. This is table 18.2, and it shows you some functional group conversions that you can do as a student in this class that change directing effects, right? Would go from a meta to an ortho para director, or would go from an ortho para director to a meta director. Let's take a look. And again, these are all reactions that you know. The first one is reduction of a nitro, right? We just talked about this. If you take a nitro, which is a meta director, and you reduce it using zinc or iron and HCl, then you treat it with sodium hydroxide, you end up with an aniline derivative. But here we have a lone pair on the nitrogen, so that's going to be an ortho para director, right? Remember, that lone pair dumps electron density into the ring, right, via resonance, whereas a nitro group is strongly electron withdrawing. So the nitro group is a meta director. Again, the amine is an ortho para director, kind of cool. Let's look at this one down here. If you have an acyl group, that's a meta director. Why? Because this is sucking electron density out of the ring, so to speak. You can do a Clementine reduction. So Clementine reduction using the zinc mercury amalgam. That's what that means when you have the mercury in brackets there. Hydrochloric acid and heat. And then you end up with an alkyl group, which is an ortho para director. It's weak. What else? Let's go to the other side. If you start with a molecule that has just an alkyl group, you've got to have at least one hydrogen here, but you can do an oxidation to produce benzoic acid, and benzoic acid has a carboxyl group, which is a meta director, right? The original alkyl group was an ortho para director. And then finally, this is the last one, and this one, I told you on the last slide that it was going to show up again today. If you take that toluene, right, the methyl group here, and you treat it with excess, so you got to treat it with a lot of MBS, you just do bromination after successive bromination to make a tribromomethyl. And remember, that's so strongly electron withdrawing that it's a strong deactivator, and it is a meta director. All right, and these are just all things that you want to have in your hat. You know, I even have a note here on my slides. It says, you know, the book doesn't really mention this in detail. It just kind of surprises you with it in chapter 18. I think this reaction does show up again later on in the carboxylic acids chapter, but anyhow, something to look forward to, right? Well, with all that in mind, and we're still on the synthesis strategies, right? If I was to ask you, you know, I want you to make this molecule for me. Well, the problem here is that you've got an ortho para director here, and then you've got another ortho para director there. How would you get them in the meta, you know, in meta substituted? Well, if you put a nitro group here first, right? I'm just thinking about retrosynthesis. If this was a nitro group, that's a meta director, right? Well, then I could reduce it after, couldn't I, right? Well, here's the synthesis outlined here at the bottom. Right, if you started with benzene and you do a nitration, again, that's a meta director. And so then you could install the chlorine, right? And then finally, you could do this reduction. You can see that this would not get you, this is not the right order, is it? Right, because now, if you do the reduction too early, then you end up converting that nitro group to an amine, which is an ortho-pair director. So what's the correct order? Let's go over here and take a look. The correct order is nitration, followed by chlorination or halogenation, followed by reduction. Okay, and the reduction is a two-step process, right? You have the reduction, then you got to treat it with base because you produce an aniline. All right, and one thing that you're going to see, and this is what makes chapter 18 a challenging chapter, in my opinion. Students at this point of Chemistry 3111 are usually pretty darn good at memorizing all the new reactions. They're usually like, yeah, I got it. The problem is this, is that if you change the order of the reactions, it changes the substitution pattern in most cases. Not all cases, but most of the time. And this is why you have to be really, really on your toes. Okay? Well, I told you earlier that, you know, you learn all the rules in organic chemistry, and then you learn the exceptions to those rules. Well, the next two slides don't cover necessarily exceptions, but they do cover what are called limitations, right? Dirty Harry said, I don't know which movie it was, the first one, second one, or whatever, but Dirty Harry said, a man's got to know his limitations, and we'll phrase it another way. You know, a human has to know their limitations. A Chemistry 3111 student, right? You've got to know the limitations that have to be considered when you're planning a synthesis. And let me tell you something right now, that we only learn a few limitations. I'm here to tell you, my friends, that in organic chemistry, and if you're planning a synthesis, oh man, it's like Mike Tyson said, everybody's got plans until they get hit, right? Well, the same thing can occur in organic synthesis. I can't tell you how many times in my life I planned out a synthesis, it looked perfect on paper, and then when I went to try it, it was like, bam, you know, Mike Tyson stepped in and ruined the whole thing, you know? And so we need to know a few limitations. Well, the first one is about nitration, right? We learned nitration. How do you do a nitration? You take aromatic ring, treat it with nitric acid, sulfuric acid, you make your nitronium ion. The problem is you can't do a nitration if you've already got an amine on the ring. The reason why is that this group, the amino group, gets oxidized in the presence of nitric acid and sulfuric acid. So that's a limitation. I can't give you any better advice than you've just got to memorize the rule, right? It's just part of the rules of synthesis. Let me show you, there's another one, okay? The next one, Friedel Crafts, right? Remember we talked about Friedel Crafts reactions? Well, a Friedel Crafts reaction, which are really cool reactions, the problem with those is that they don't work if the ring is moderately or strongly deactivated. If it's weakly deactivated, they will work. But if you have something that's a moderate deactivator, so what were those? Those were groups that had a pi bond attached to the atom that was directly attached to the aromatic ring, like a ketone or a carboxylic acid, or a nitrile was another one, amide, sulfonic acid, stuff like that won't work. And if you have a strong deactivator, it doesn't work in that case too. Okay, so that's a serious limitation, because the Friedel Crafts is kind of a go-to for several syntheses that we're going to look at in this chapter. Okay, well, with all that in mind, and that's a lot on our minds, isn't it? That's a lot of reactions, and those limitations can creep up on you and just, you know. With all that in mind, let's take a look at question 18.26 and 18.28. So we're still on section 18.12, and really this problem and this problem, we're really just going to kind of tackle some problems where we have to apply everything that we've learned in this chapter. So these are really important questions. 18.26 says, starting with benzene and any other reagents, design or synthesis of each of the following compounds. Note some of these problems have more than one plausible answer. You're going to see this come up all the time from now on, right? That you're going to answer a question correctly, and then a friend might have a different answer, and it's still correct. Okay. In the interest of room, I'm just going to move over to a blank document here, because I know myself and I will run out of space. Let's see here. Do I have room on any of these? There we go. All kinds of space here. All right. So this is 18.26. 18.26. And we want to make this compound. So this would be ortho-bromo-aniline. So we've got an amine here, and we've got a bromine here. The only way that we know how to install an amino group is by nitration and reduction, right? And our starting material is benzene, okay? We're starting it with benzene. So at some point we're going to do a nitration, and at some point we're going to do a reduction. What else? Both of these groups are ortho-para directors, aren't they? Right? They're both ortho-para directors. Well, let's think about it. What would I want to do first? Well, if I install a nitro group first, right? If I was to take this, and if I was to just install a nitro group first, right, I'd run into problems, wouldn't I? Because then if I just go ahead and I install a nitro group first, that's a meta director. Okay, so I think a better choice would be for us to install the bromine first, okay, because at least that's an ortho director, and this is an ortho position. So let's do that. So if we install a bromine, so bromine and iron 3 bromide, we would have our bromine in this position. Now, if we want to nitrate it and get it into this position, we've got a problem, don't we? Because if we just take this and we just treat it with plain old nitration conditions, right? Nitric acid and sulfuric acid, what's the problem? Is that we're mostly going to get the nitration occurring at the para position, right? We're going to get, or at best, we're going to get a mixture. So how would I force the nitration to occur exclusively at the ortho position? Does anybody have an idea? What kind of strategy I might want to take here? Yeah, exactly. You're all right. And thank you for listening. Thank you for paying close attention, you guys. That's great. The answer is fuming sulfuric acid, isn't it? Fuming sulfuric acid. I'm going to install a blocking group, aren't I? We're starting with the heavy stuff right away, right? Adding extra atoms that we're going to remove in the end. Remember atom economy? Right, from organic chemistry 1. Well, this doesn't have very good atom economy, does it? Because we're going to blow this off after. Right, but now we've got something that's activating to the meta position, or its meta position, and the bromine is activating to the same position. So now we can do the nitration. Right, now we'll take this and we'll treat it with nitric acid and sulfuric acid. We'll install the nitro group. So let's do that. We've got the nitro group, got the bromine here, and we've got the sulfonic acid, like that. Perfect. Now, we could treat it with dilute sulfuric acid, remove the blocking group, or we could do the reduction first and then treat it with sulfuric acid after. It doesn't really make any difference. I'm going to get rid of the blocking group first. So I'll put dilute sulfuric acid. So that's going to give me this compound. There I have my bromine and my nitro group. And then in the last step, I do the reduction. So I'll use iron and HCl in the first step. And then I'll use sodium hydroxide, of course, in the last step. And that, my friends, will give you the final product where the bromine and the amine are ortho to each other. All right, there's a synthesis of ortho-bromo-aniline. So this is 18.26a. Let's move on to another one. This is 18.26. Which one was the next one? B. So 18.26b. We're asked to make this cool compound where you have a nitro group, okay, and you have a chlorine, and they're meta to each other. Okay, well, how would we do this? Well, the nitro group is a meta director and the chlorine is an ortho-para director. So I don't like to use the word, simple in organic chemistry because it's not simple, but I think we should start with installing the nitro group first, because then at least we'll have a meta director. So let's do that. So we start with benzene. What are the conditions for nitration? You've got to have them memorized. I'll give you a reagent sheet, but remember, I won't tell you what they're used for. Right? So there we go. So we're going to have our nitro group installed. And then next, to install the chlorine, we're going to use chlorine and aluminum chloride. You could use iron 3 bromide, doesn't matter. And there you go. This is a much faster problem, isn't it? We've got the chlorine installed, and we've got our nitro, which is meta to it. And there we go. That's it. A two-step synthesis. Boy, that first one was a real barn burner, wasn't it? Okay, let's take a look at 18.26C. I'm just going to scroll down here and give us some more room. 18.26C. We've got, what is it, para-butyl aniline, I guess you'd call this. So it's an aniline derivative, and then we have 1, 2, 3. So parapropyl aniline is what this would be called. Okay, so we're going to start with benzene. All right. Well, the thing is, we can install the propyl using a Friedel Crafts reaction. We can install the amine using nitration and reduction. However, if we look at their activating abilities, this is a strong activator, right? Strong activator, which is an ortho-para director, and this is a weak activator. So a weak activator, which is an ortho-para director. So I think we should put the strong activator in first because it's more strongly activating, right? We'll end up with a higher yield. So why don't we install the amine first? So how would we install the amine? The first thing we want to do is nitration, which seems to be coming up a lot in these problems. So let's throw in our nitro group. You notice that I'm drawing the abridged structure of benzene here with just the circle to represent all of the pi electrons. It's just a bit of a time saver. Then we reduce that with iron and HCl. And then in the second step, we treat that with sodium hydroxide to deprotonate the aniline ion that is produced. So we end up with our aniline. We have our strong activator, our nitrogen, the lone pair. So now, how would we install the propyl group? And this is what I'd like to ask your help on. Could anybody tell me how I would install the propyl group? And it's not a trick, and if you can't come up with the whole name, just part of it. Could anybody tell me how to install a propyl group? Just 3 carbons in a row. There's a name for the reaction. It's named after 2 organic chemists who have long since shuffled off this mortal coil. Not a, oh, sorry, I can't see what you're saying here. There we go. Yes, that's perfect. That's perfect. Spelling is unimportant. Okay, Friedel Crafts, absolutely, but it's not Friedel Crafts alkylation, is it? If you were to try to do this using Friedel Crafts alkylation, so propyl chloride and aluminum chloride, it won't work, right? Because you get rearrangement of the carbocation. So in this case, what you'll want to do is you want to do Friedel Crafts acylation, and then we will reduce the carbonyl. So we're going to treat this with propyl. This would be called propionyl chloride, and it's neither here nor there. We learned about the nomenclature of acid chlorides in the carboxylic acid chapter. But there we go. Then we have this. There we go. Like that. And then the last thing we need to do is a Clementine reduction, for which we use the zinc mercury amalgam in HCl, and we can heat that up. All right. And there we go. Am I missing anything? Nope. There we go. So that would reduce the propyl group. 1, 2, 3. And there's our amine like that. Okay. I want to just mention one more thing here, though. Okay. There is an alternative to this. I would say that, if somebody was to answer this, if you were practicing at home and you said, first, I'll do the Friedel Crafts acylation. Okay. I'll do that first. Then I'll do the Clementine Reduction, which would just install the propyl group. That's an ortho para director. It's going to direct to the para position because it's more sterically hindered than a methyl group. Then I'm going to do the nitration. Then I'm going to do the reduction. I would accept that. Okay, if we were doing paper quizzes and somebody gave me that, I would say there's nothing wrong with that. And then sodium hydroxide in the last step. I'd say that would work too. The only it's not a problem, but the difference is that this is not going to be as high yielding. Okay, this will work in a higher yield. Okay, so we'll put here highest yield synthesis. That other one is going to work, but this is so strongly activating that this reaction is going to go in a higher percent yield than the nitration is going to occur when you've only got a propyl group on there. Okay, so that's kind of my answer right there. Okay, and that's all for question 18.26. Let's take a look at 18.28. 18.28, I'm not going to go back to it because it's basically the same type of question. It's just, tell me a synthesis or show me a synthesis for this reaction or for this of this molecule, I should say. But now we're having, 3 substituents on a ring. So here's our benzene ring. We've got an isopropyl group. We've got a bromine. And then we have an acyl group here. Well, if we just think about this in terms of retrosynthesis, the only way that we know how to install this is with bromine, and we could use aluminum bromide, whatever. Okay. The only way that we know how to install this is with this molecule. This is called acetyl chloride or acetyl chloride and aluminum trichloride. That's a Friedel Crafts acylation. And the only way that we know to install this is with Friedel Crafts alkylation of isopropyl chloride and aluminum chloride. So then the question becomes, we know how to do all the reactions. It's just which one do you do first? Right? Well, the isopropyl group is an ortho para director. The acyl group is a meta director. And then the bromine is an ortho para director. All right, so this is an ortho para director too. But what I suggest that we do is that we install the isopropyl group first. Because if we want to install this at the meta position, right, this is a pretty big group. So it's going to preferentially do the acylation at the meta position. All right. Then if I have the isopropyl group and the acyl group installed, they're both going to direct to this position. So I could do the bromination last. If you're thinking, well, I could do the bromination first. Well, the problem with that is there's no way to get this installed here. Then you'd have to get a blocking group in there and all this stuff. It would be way more complex than just a 3-step synthesis. So we're going to go with the shortest synthesis, which would be first to install the isopropyl group. So using isopropyl chloride and aluminum chloride is our Lewis acid. That would give us isopropyl benzene, which again, I keep telling you is called cumene. There we go. Then we would do the Friedel Crafts acylation. So we would use this molecule, this acid chloride. It's got the 2 carbons. And we use aluminum chloride as our Lewis acid. That would give us this molecule. Right? And then the last thing that we would do is the bromination, right? Because both of these groups are directing to this position. So what do? We take the molecule and we treat it with bromine and iron 3 bromide. That, and there you have it, my friends. That's all there is to it. It's all about making good decisions, right? Just like that, 3-step synthesis. Okay, let's go back to the slide deck here quickly. And we've covered a lot of the material, but you'll notice that this chapter, again, is unique if you compare it with all the other chapters that we look at, because usually, let's say in chapter 11 or 12 or, I don't know, 16, for example, right? Whenever you get to the section on synthesis strategies, it was always the end. Well, here in chapter 18, we move on, and there's 3 more sections after the synthesis strategies section. The reason why is because the first major chunk of the chapter dealt with what? Electrophilic aromatic substitution, didn't it? Right, up till now, all we've been talking about is electrophilic aromatic substitution. That's where the aromatic ring acted as a nucleophile, and it reacted with an electrophile. Well, in section 18.3, we look at something totally new. It's called nucleophilic aromatic substitution. So now, our aromatic ring is going to be acting as an electrophile, and it's going to be attacked by a nucleophile. So something completely different. If you take a look at this reaction here, you take para-nitrobromobenzene, you treat it with sodium hydroxide, 70 degrees Celsius, and then you treat it with acid after, and you end up with a phenol. Well, what happened? How did you replace the bromine with the hydroxyl to form the phenol? The reason why you were able to do it is because the hydroxyl acted as a nucleophile. So it literally attacked the aromatic ring, and you ended up losing the bromine. Now, that arrow is not correct. It doesn't work like an SN2 reaction. Otherwise, it would have been learned way back in chapter 7. No, we have to look at a new mechanism for nucleophilic aromatic substitution, and we call that mechanism an SNAR mechanism. So SNAR, right? You've learned SN1, you learned SN2. Now you're learning, SNAR, something completely different. And in order for an SNAR reaction to take place, there's 3 requirements. You've got to be aware of these. I remember a number of years ago on the ACS final exam in the classroom, when I looked at the exam, one of the questions dealt with an SNAR reaction. It says the benzene ring has got to have a strong electron withdrawing group. All right, what were the strong electron withdrawing groups? Something like a nitro group, or a trihalomethyl group, okay, or a nitrogen with a positive charge. The ring's got to have a good leaving group. It's usually a halide in chemistry 3111. So it's usually, I'd say, I think in all the examples, come on, where's my pen? It's either got to be a, well, it's either going to be a chloride, bromide, or an iodide, anyhow. And then the leaving group, and this is the key part, okay? The leaving group, okay, which we'll call X, it's got to be positioned para or ortho to the electron withdrawing group. So you've got the electron withdrawing group. The leaving group has to be either ortho, okay? I'll just copy this to draw the other possibility, or it can be para, okay? So it doesn't work if it's meta. So if it's meta, no dice, as Charles Bronson would say. All right, there we go. So again, if the leaving group is meta to the electron withdrawing group, here's your electron withdrawing group, here's your leaving group, they are meta to one another, you get no reaction, right? So with the electron withdrawing group in the meta position, it is unable to stabilize what's called the Meisenheimer Complex intermediate. Now, if you're like, what the heck's a Meisenheimer? Okay, well, it's kind of like the SNAR equivalent of a sigma complex. You remember how a sigma complex had a positive charge in the aromatic ring? Well, a Meisenheimer complex results after nucleophilic attack, okay, on the aromatic ring, not the aromatic ring acting as a nucleophile, and so it's got a negative charge in the aromatic ring. Take a look. Here's the first step of the mechanism, the nucleophilic attack. So your hydroxyl, whoop, attacks here. But I told you the leaving group just doesn't simply leave like that. That doesn't happen. You actually can push electrons and show that electron density actually ends up inside the aromatic ring, and that is what we call the Meisenheimer Complex. Now, the reason why you have to have an electron withdrawing group like a nitro group, either ortho or para, to the leaving group rather, is because what you see is that the negative charge is delocalized to this carbon, but then it can go down onto the nitro group or into the nitro group as well. So in essence, the nitro group can function as a reservoir for the negative charge. You see, we'll call it a negative charge reservoir. Now, Skylar, you must be the kind of person who's into wrestling, you know, in the WWE wrestling, you know, when they throw a guy against the ropes, right, and he rebounds off the ropes and pow, hits this. You know, that's what I think about every time I see the SNAR mechanism, right? Because it's kind of like you got the first wrestler coming in, right? He hits the, you know, he hits this guy, but then the other guy goes, whoa, and he gets rebounded way into the back of the ropes. Okay, and then kapow, right? Then the chloride gets ejected. Now, I don't know if that's the best analogy, but hey, you know, I study I love organic chemistry and I study it for a living. I'm a little strange, okay? So that's what I think about every time I see an SNAR mechanism. And this is one of my favorite mechanisms that we learn in this class. It's just the loss of leaving group, right, involves 4 arrows. You can see how that negative charge goes all the way from this oxygen, and it's like, oh yeah, just watch me. Boom, 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 and pow. And it kicks out the leaving group like that. One of the coolest mechanisms that we look at, okay? So the Meisenheimer complex, again, it's the resonance hybrid that results after the nucleophilic attack in an SNAR reaction. So there you go. That's an SNAR reaction. Now, if you're wondering what the hell was the point of the acid, well, let's think about it here. If you are treating this with sodium hydroxide, well, what would happen if you took phenol, right? And I'm just going to scribble this down here. If you took phenol and you put it in sodium hydroxide, okay, what are you going to end up with? You're going to end up with phenoxide and water. Well, water has a pK of what? 15.7, and phenol has a pK of 10. So the equilibrium is going to lie to the side of the phenoxide, and therefore you have to have 2 steps, right? You've got to, in the first step, treat it with the nucleophile, which in this case is the hydroxide, but then you end up with the phenoxide, not the phenol. So then in the second step, you got to treat it with water to protonate it to make the phenol derivative. Remember, this is called a phenoxide, and this is called a phenol. A phenol and a phenoxide. All right, I don't know what that was. All right, but I'm going to assume that you can still all see my screen. Maybe it was some kind of higher power telling me I need to stop talking about organic chemistry. Well, tell you what we'll do then. We could take a break, and I would like you to both try, or to try both of question 18.30, which you can see is a very short problem. But you can see we've got a strong electron withdrawing group. Here we've got 2 halogens. One is para to the strong electron withdrawing group. The other one is meta. And we've got a sweet, sweet nucleophile here, right? We've got methoxide. Okay. We've got the sodium cation. Okay, so I want you to predict the product. You could even practice drawing the mechanism maybe of the SNAR. I'll give you a clue. Since this is the SNAR section, this is an SNAR reaction, which you probably guessed. And I'd also like you to try 18.31. It says starting with benzene and anything else. Design a synthesis of the following compound. Now you probably notice that you've got 2 strong activators that are both ortho and para. So there's some interesting chemistry that must be occurring here. But I'll give you a clue. You're going to have to use an SNAR at some point to get this synthesis completed. SNAR again. All right. And after we finish those 2 questions, we've only got one more new reaction to look at. It's a quick one. It's section 18.14, which deals with one more reaction. It's called an elimination addition reaction. And then after that, section 18.15 is just kind of taking a look at mechanisms. You know, is this a electrophilic aromatic substitution? Is this an SNAR? Or is this an elimination addition reaction?